Another one is another bottle of hydrogen peroxide. Its face is life, mysteriously vanishing.
It's true, detective. This has been happening all the time. The bubblings, the potency, it just fades. We need to crack this before it's too late.
Fear not, people. We're not dealing with a criminal mastermind. It is just a natural phenomenon, to be precise, a first-order phenomenon.
First order, you say? Explain yourself, forensic analyst.
Thinking of the first order of differential equation, it describes how much something is transformed, whereas the rate of change depends on the quantity of that something. To make it clear, imagine a leaky bucket. The rate of change of water loose from the bucket depends on the quantity of the water in the bucket.
So, the vanishing bubbles, it's like the hydrogen peroxide is leaking away at a rate proportional to how much hydrogen peroxide is left.
Yup, precisely. This is what we call a first-order phenomenon. These equations are our prime suspect in solving numerous mysteries in physics, engineering, and even our little chemical drama here.
Our primary suspect, hydrogen peroxide H2O2, known for its versatility but also instability.
We have observed it consistently breaking down into water and oxygen gas. So, the vanishing bubbles is the oxygen gas escaping.
So the problem we face is this. How do we quantify this decomposition? How can we predict exactly when and how much H2O2 will be left? We need a mathematical model to crack this case wide open.
Our first clue is a rate law for a first-order reaction. So, the rate of change of the concentration of hydrogen peroxide is directly proportional to its current concentration. Hence, we introduce K as a rate constant for this equation, and finally, we can get the final equations.
This is a separable differential equation, detective. We can gather all the hydrogen peroxide terms on one side and the time terms on the others, like separating evidence.
Alright, integration. That's like piecing the fragments of evidence, isn't it?
Yep, exactly. We need to integrate both sides of this equation to get ln H2O2 equals to negative Kt plus C, where C is a constant.
To get rid of the pesky logarithm, we use the inverse operation, exponentiation.
So, e power of C is just another constant, right? Let's call it A, the initial concentration. Perhaps?
Spot on, detective. When T equals to 0, we need to substitute the 0 in the equation, And finally, we can get A as our initial concentration of the hydrogen peroxide.
And thus, the final solution, the mathematical confession of our vanishing bubbles is
So this equation tells us the concentration of H2O2 at any time. Given its initial amount and the rate constant, the case is closed. Through the meticulous application of first-order ordinary differential equation, we have not only understood why the hydrogen peroxide decomposes, but how it does so.
this isn't just about a single bottle. The same mathematical approach helps us to predict drug decay in the body, radioactive decay, and even the cooling of a hot cup of coffee.
It is a testament to the power of mathematics in unraveling the mysteries of the world. From vanishing bubbles to global phenomena, ODE is the framework to understand change.
Our investigation couldn't have been completed without this crucial resource.
And a big thank you to everyone who assisted in this complex case, especially to Zafri, Rosie, Shifa, Esther, and Ho. Your participation made this video possible.
And of course, to our esteemed lecturer, Dr. Ang Tao Kiong, for guiding our investigative journey. That's all from us. Thank you so much.